Hi, in this video, we want to take a look at some variations on principal component analysis. All right, so what we want to do, we want to be able to compute principal component analysis, but we want a little bit more control over how we go about this. Like maybe I'm not satisfied with how PCA is coming out with my data. Maybe I'm worried about outliers. Maybe I want to make sure that I want to take control over my loadings. Well, in this video, we're going to talk about ways that we can go about doing this. Now, this example is taken from Modern Psychometrics with R. It's by Mayer and it is a Springer textbook. Here is the website for the code that I'm modifying to be able to do this. All right, so in this video, we're going to look at really two aspects of variations on principal component analysis. All right, so conceptually, the first one really isn't a variation of PCA. It's an alternative way to compute it. All right, so this alternative way to compute it is that instead of putting data into the function that computes the principal component analysis, we're just going to put a covariance matrix in. So normally what we've done is we take data, we put it into print comp or PR comp in R, and it spits out the PCA for us. Okay, now let's change this up a little bit. Instead of putting the data in to the function, I'm going to put a covariance matrix in. Okay, now why would this be an extension, a variation of PCA? Well, this way, any technique that I can come up with as an alternative or special version of covariance calculations is going to basically translate into a special version of principal component analysis. All right, so let's say I want to use a robust technique for computing the covariance, then ultimately I'm going to have a more robust version of PCA. Also, maybe I want to choose a covariance calculation that is tailored to the data I believe I have, the distribution. So maybe if I'm dealing, I believe I have multivariate normal, I could work with something that is more tailored to take full advantage of that. Because remember that regular old PCA and covariance does not take into account the distribution. Now, another way I could go about it is if I want to use the t-distribution for my covariance estimation. Now, it will be similar to Gaussian, but you know that there's going to be a more dispersion aspect going on. And now, the other thing that we're going to look at in this video is basically lasso for PCA. All right, so if you've never worked with lasso is where I go into regression and I try to make sure that I get a good fitting model, but my coefficients don't get too big. By not having the coefficients not get too big, I'm making sure that I don't overfit. All right, so what we want to do here is to protect ourselves from overfitting on our principal component analysis. We're going to use a lasso technique. Either I'm going to declare that a number of non-zero coefficients I have in my loadings, or I'm going to define a penalty term. In the example we do, we're going to define the number of non-zero loadings. Now, something that's nice about this is that when I have zero values in my loadings, I ignore those, and it's much easier to interpret what the loadings are. All right, so something that we also need to think about whenever I'm working in principal component analysis, remember that standard deviation corresponds to, and this is I'm kind of fudging the math here, but just kind of think of it this way. It's not 100% precise, but the standard deviation of a column corresponds to how much weight, how much influence that column has in our principal component analysis. All right, well, if you've worked it with PCA for a while, you know that the vast majority of times we want to standardize our data. We subtract the mean, divide by the standard deviation. This way, each column has equal influence. Well, now if I'm handing a covariance matrix, I can't, I'm not standardizing anything. And with a covariance matrix, we intentionally do not have standard deviation of 1 because that is not how we compute it. All right. So what we can do, if I want to make sure that my columns are standardized, for the amount of influence they have in PCA, I just inside print comp, I put core equals true. All right, so if core equals false, it's going to take the raw covariance matrix and compute it. Now, if I put core equals true, it's going to take that covariance matrix, convert it to a correlation matrix, and then it's going to run it. Each column will have equal weight. All right, so for this example, we're going to use the privacy data set. So this is talking about the advantages and disadvantages of privacy on the internet. It's in the mPsychoR package. All right, and so now I'm going to run through several examples where basically I'm computing the covariance matrix in a different manner, and then I get PCA. All right, so for this first one, what I want to do is I want to put smallest volume confidence ellipsoids. All right, so you know about confidence intervals, hopefully at this point. And confidence interval is for one dimension. Well, when I get into multiple dimensions, the geometry gets more complicated. So what we would like, in a way, we would like to have a circle if it was like 2 dimensions, a sphere if it's 3 dimensions, and then like a higher dimensional sphere if it's even higher than that. And that works out really great, but that doesn't actually fit as well as it could. So what I'm going to do instead of having like so in 2 dimensions, instead of having a circle, I'm going to go with an ellipsoid, ellipse. I'm going to go with an ellipse. So instead of going with a circle, I'm going to stretch it out where the data is long, and I'm going to go narrow when the data is narrow. And so I'm going to get the best ellipse that I can find to go around most of the data. So like 95% of the data. So I want the smallest, so if it's 2 dimensions, I want the smallest ellipse that will have 95% of the data within it, 5% outside if I'm doing a 95% confidence ellipse. Okay, well, in higher dimensions, it gets more complicated, but conceptually it's very similar, that instead of having an ellipse, I have an ellipsoid because it's higher dimensions, and I want the smallest volume ellipsoid that will capture the percentage of data that I want. All right, so here we're going to be using the mass package, and the author in this one went ahead and rescaled privacy. And so with the core equals true, I probably didn't need to do it, but I think it's actually a good call to do. I think you should rescale your data on this one. Now, something about this though is that rescaling can change features of your ellipsoid. If you're going to be changing features of your ellipsoid, this can change things about your output, and you don't really know it unless you go in and start digging in, rolling up those sleeves and looking at it. So remember, rescaling your data changes your ellipsoids. This is an important aspect. Like if you do model-based clustering, we generally don't rescale our data because of this particular point. And model-based clustering uses the ellipsoids. That's why I'm bringing it up. All right, so what this does, this technique filters out data that is outside of the ellipsoid. All right, and you can't see it on my screen, but if you go through the code and you print this up and you go through it, you can get an idea of where that ellipsoid is in relation to each of the pairs. I've got blue for inside the ellipse, gray for outside. So anything that's gray for a data point is something that was kicked out of the computation. If it's blue, it's inside the computation. All right, so now, once I have that, you'll notice that I put covariance matrix is the parameter. I don't actually put in the data. And now, once I've done that, this is just a standard, principal component analysis, but I don't have the original data. If I want to get the PCA of the data, I have to use the predict function. That's easy peasy, lemon squeezy. I just go predict, I pass print comp, and then I tell it the new data is privacy. And here we can see the results. I only plotted the first three. I felt like that was sufficient. But when you look through, you can kind of see like a clumping here, and you can see a clumping here, and a clumping. And as you look through, when you see things off on the edge like this, that, well, that looks like it was outside of that ellipse. This makes sense to me. All right, so now I'm going to do something very similar, but I'm going to use a distribution assumption to compute my ellipsoid. So previously, the ellipse was actually computed based off the data. And there was no assumption about the shape or the distribution of the data. Here, we're going to use the assumption that we have multivariate normal distribution, and I'm going to use that as insight into what the best ellipsoid is. And so here, the parameter for this within the mass covariance robust calculations MCD. All right, so this stands within the mass package. This is covariance robust because I'm filtering out the outlier values. And so here, this is whenever I'm using multivariate normal distribution to compute my ellipsoids. This MVE is whenever I am using confidence intervals or confidence ellipsoids without considering the distribution. And the example is exactly the same as it was. I get a covariance matrix. Here we are rescaling the data, which is something I would definitely want to double check on that to see if that changes how things look. Here I'm just plotting to show which data points were outside the computations and which ones were in. Oh, and if you look at the default setting for covariance robust in the mass package, it's a little bit more than 50% of your data if you're in big N, small p. It's N plus p, like +1 divided by 2, something like that. But if I'm in big N, small p, it's a little bit more than half of my data. And so now once I get my principal component calculations done, I use the predict function because remember, the print comp did not have the actual data. Since it didn't have the data, it can't tell me what the transformed values are if I'm trying to use this for like dimension reduction or machine learning. Here we can plot and just kind of see how things look. This looks very similar to the previous one. Conceptually, they are very similar. Now, we can also just use classical covariance estimate. So in this situation, I'm using the same function, but I put in method equals classical. And so I just want the regular covariance. Don't worry about robust, just compute it, spit it out at me. So all the values are blue when I look at my plots because all the values were included in the computation. I did not filter any data on this one. And here we get the principal components. Now, the mass package also gives us the opportunity to use not just the Gaussian distribution, but multivariate T distribution. And so this distribution will be more dispersed out. So that's just something to be mindful of. If I want my ellipsoids to be bigger for the same percentage, then multivariate T will be bigger than the Gaussian because of how the tails are set up. Not tails, but multivariate. Think tails for marginal. All right. And so once again, I'm plotting it. no values were, so some values were filtered out. It's hard to see. Oh, none of them were filtered out. Oh, because this is not using confidence ellipsoids. This is using an alternative estimation of covariance. I misspoke. All right, so this technique is using a different covariance estimate that is based off of multivariate t-distribution. So no values are filtered out, but everything runs out to be just the same. So with this, what I'm doing is I'm changing how I compute my covariance matrix, and then I'm taking advantage of that flexibility to give me a better principal component for my project. All right, the next one, we want to consider that, you know what, when I look at these loadings, I don't want to have any large coefficients. I don't want to overfit. I want to protect myself from that. And also, if a loading is like close to zero, I would rather just kick it out and not even have to look at it. I just want to look at what is relevant for each individual component. All right, so what we're going to do, we're going to have lasso to the rescue. Now, I'm not talking about Wonder Woman's lasso. I'm talking about lasso from penalized regression. Okay, so what we're going to do is we're going to apply a penalty parameter to the coefficients. So if the coefficients are large, we're going to get hit with a penalty. And how much penalty we're willing to tolerate depends on what we put in. All right, so now something that's nice about the flexibility of this is that I can assign different penalties for each and every component. So I could put like 0 penalty on several of them and then put a huge penalty on only one of them. I have that level of flexibility if that's appropriate for my project. Now, another way I could go, so the penalty way is sparse equals penalty. And in this, we put in a non-zero vector. So actually, I can't put in 0 penalty, but nearly 0. I need to put a non-zero vector for the penalty for to kind of force the shrinkage. Now, another way I can go is that I can dictate how many non-zero entries I want for the loadings inside each component. All right, so if I know that, hey, I'm just going to ignore anything more than like 4 loadings in a component, then you know what, I'm just going to set it equal to 4 and let the machine find the best values, considering that it can only have 4. I like this one a lot because this is going to be really easy to interpret, easy to set up. And so if I want to control the number of non-zero entries, I use the var num parameter. And para, I have to enter an integer vector defining the number of non-zero loadings. So in ElasticNet, we're using SPCA. Once again, I'm rescaling my data. Now here, I don't have as many concerns about this because we don't have any distribution ellipsoids going on. K says compute 3 components. And we're saying that we want to control the number of non-zero loading coefficients. And we want 3 non-zero, 4 non-zero, 3 non-zero. So the first component has 3 non-zero, second component has 4 non-zero, and the last component has 3 non-zero. So now I can get it and I can get the results here. You'll notice that the top 3 on PC1 are non-zero, everything else is 0. In PC2, the last 4 are non-zero, the rest are 0. And then these middle 3 are the 0. And you'll notice that they're completely separated out. So effectively, this has partitioned my columns into ones that are like working together to evaluate the same thing. And so this makes it very easy to interpret that I have, boom, these 3 are measuring something similar together. These 3 are measuring something similar. And I know that these are about the advantages. So the first 6 columns of my data are about the advantages of privacy. And then the last 4 are about the disadvantages of privacy. And we can see, boom, those are all being put together. And so the second principal component is looking at basically all possible disadvantages of privacy on the internet. The first principal component looks at the first 3 advantages. So like probably there's like, if I was to look at the original data, I'd be able to say, all right, this is this category of advantage. And here, this is going to be a different category of advantage. All right, well, that's all I've got for you. Take care and goodbye.